For both the summer jobs problem and the volleyball problem, you saw that it sometimes is necessary to quantify or rescale information. For example, you sometimes need to operationally define constructs that cannot be measured directly. Instances of this occurred when you developed a formula to define worker productivity in the summer jobs problem, and it also occurred when you developed formulas to define good volleyball playing ability and fair teams in the volleyball problem. Second, you sometimes need to quantify qualitative information. For example, in the volleyball problem, you had to assign quantities to qualitative information when you developed ways to use information from tryouts, to assign scores to coaches' comments, and to serving ability, and to returning ability. Third, you sometimes need to rescale quantitative information. For example, this occurred in the volleyball problem, when you developed ways to combine or compare running scores and jumping scores. Points of all of these examples are that 1. Every statistical procedure is based on a description or an interpretation or a model of the situation. 2. Different descriptions involve different assumptions about the kind of mathematical objects and relations, interactions, and patterns that you consider to be important. 3. Different assumptions often make big differences in results that you produce. Next, we'll see that when you imagine that you are just calculating with numbers, you also might be defining relationships among subjects of your analysis. This Tinker Plots worksheet shows information about the scores of a sample of 12 students in a pottery class. To see how the sampler works, let's run it. As the students create different kinds of pottery, their teacher has given them 2 scores. One score is a quantity score, for how much they produce, and the other score is a quality score, for the quality of their work. Notice how these 2 scores are recorded in both the table and the graph. This system of scoring worked well in the past because, at the end of the semester, the teacher only gave grades for passing or failing the course. But now, more detailed decisions need to be made, because several local stores have offered to provide prizes for students, according to their ranking in the class. The problem is that the teacher has 2 scores for each student, and now she needs to combine these into a single score. Her friend, the English teacher, said, "Just add the scores. That's what I always do." But another friend, the economics teacher, said, "Multiply the 2 scores. This gives total quality, because if you do 2 or 3 times as much work at some level of quality, then you deserve 2 or 3 times as much credit." Then, a math teacher said, "No, you should divide the quality score by the quantity score. This will tell you the quality per unit of quantity." And, the tennis coach said, "In tennis, when the score is 30 love, this doesn't mean that you only have scored 30 points. It just means that you are 30 points ahead. So, I think you should subtract the quantity score from the quantity. I think this is like factoring out the quantity score to focus mainly on quality." And finally, the science teacher said, "You should calculate the vector sum of quality and quantity, because quality and quantity are different dimensions, and you want to combine them." Now, the art teacher was even more confused, because she noticed that the way students rank depends a lot on which method is used to combine scores. To see this, just drag down the results into the graph as the bottom of the worksheet. And, notice how the ranking of the students changes for each method that is used. To see more about why this is happening, let's consider 100 students who are graded on a scale of 1 to 10 for both quantity and quality. And, let's generate the data so that we get all possible combinations of scores that can occur. To do this, we simply use a counter instead of a mixer to generate scores for students. Now, if we select a column of students who all have the same sum, then the other graph shows which students are being treated as if they were the same. For example, in this case, a student who gets scores of 1 and 9 is treated as being the same as a student who gets a score of 5 and 5, or a score of 9 and 1. To see what happens for the other operations, we need to look at a larger sample. So, let's consider the 10,000 possibilities that can occur if each student gets 2 scores from 1 to 100. And again, for each arithmetic operation, let's select a column of students who all get the same score, and then look in the other graph to see which people are treated as if they were the same for each operation. When we add the 2 scores, students on diagonal lines are considered to be equivalent. If we subtract, then the diagonal lines go in the other direction. If we multiply, then equivalence scores lie on curves that bend in toward the point 00 on the graph. If we divide, then equivalence scores lie along fan-shaped lines that start at the point 00. And, if we use vector sums, then equivalence scores lie on circles around the point 00. So, each time we add, subtract, multiply, or divide scores, we are also defining equivalence classes of scores which are treated as if they were the same. In fact, it's not only true that number operations may result in different equivalence classes, but we also can use equivalence classes and graphs to define number operations. For example, this graph has been divided into 5 regions. And, all of the points that lie on the inside region can be given a score of 20, with 40 for the next region, 60 for the next, 80 for the next, and 100 for the last. So, operations may define equivalence classes, or equivalence classes can be used to define operations. And both can be useful in statistics.